name's Chelsea Walling. I'm an Aquaculture Extension and Research Associate here at KSU's Aquaculture Research Center. About the university, learned enough about KSU in general. So this is our main in-person learning classroom. Then we have a distance learning classroom because we offer a lot of online coursework as well. And we can just kind of mosey through this building. There's not a ton of stuff. So in here is our fish disease diagnostics laboratory. So just like any other animal, fish can become ill. They can get bacterial infections, viral infections, often non-communicable to humans because they are poikilothermic and we are warm-blooded animals. So not a whole lot of risk of disease transfer. However, we've got, this isn't someone's one goldfish in their, little aquarium at the house. This is someone's entire livelihood. So just like a cattle farmer, chicken farmer would put medications on their feed, we can determine medications for our feed by bacterial analysis, antibiotic susceptibility testing. We'll auger plate that, do our antibiotic resistance test, figure out which medication is going to be the most effective for the disease, and then have to put that medication on the feed, which has to happen very quickly because as soon as those fish are off feed, you're just not going to get them, to get well. So that's a state-offered service. We also do a lot of water quality testing, aquatic weed management, lots of other different services that are part of our cooperative extension program. We have graduate students in here. If you are marketing a product, it needs to be done in a certified processing kitchen. My joke, I get a lot of kid tours. I say, it doesn't matter if you're greenies making jelly and selling it at the farmer's market, it needs to be done in a certified kitchen. So the only thing that can be processed in this laboratory is fish products. No one can bring in their big buck and cut it up in here. No chickens, no anything else, just fish products. But the key is food safety. So as soon as fish are sacrificed, usually by ice bath, chill kill method, that's one of our approved disposal or harvest methods. They are brought in, their fillets are removed and they're instantly dropped down to temperature. So we do lots of temperature checks, making sure everything's kept clean, sanitized, and cold. That's our goal for food safety. We'll head on out. Aquaponics team, as am I, but a lot of our products go to our local soup kitchen, or we've been a part of a local CSA recently that has been going to needs-based organizations. So
try not to step on toes.
Yeah, we don't want to sell anything. We're not trying to make a profit here. We don't want to compete with our local farmers. We would just want to add to the food sector, especially locally. So yeah, a lot of our greens and stuff like that gets donated, and then fish harvest day, everybody's got their Ziploc bags ready to get some. We can head back out the way we came in. This loading dock's just a little.
So KSU, the aquaculture program more specifically, just received a $7 million NSF grant. It's through the eRise R2 program, so it's like brand new, which is good and bad. It's great that there's a lot of leeway on what we can do with it, and it's bad because the NSF's like, we don't really know what we want out of it, so you guys are the guinea pigs. And we're like, is there like, specific checklists that you want? They're like, no, not really. We're just gonna kind of let you guys figure it out as we go. So this is now informally known as the genomics lab. So right now, all we have is Oxford Nanopore long read sequencing capability for DNA and RNA. I don't know if anybody's familiar with that or not, but it's super low cost. We're down to basically $11 to sequence any DNA sample. So this is the Oxford Nanopore Mark 1C. Yeah. So the Mark 1B is smaller. Okay. So we did 22 hours, a 22-hour run on. We barcoded 72 samples, pulled a 400 gig data set in a day. It's pretty impressive how much data we can get in a short amount of time. But that's it. We're sequencing, we can sequence whole genomes on a, iPhone, basically. So the new one's smaller. So right here's where the flow cell goes. So basically, instead of like having reagents, you're just constantly like throwing in, you have a flow cell, throw your sample in that, and that's where the sequencing actually occurs. It plugs in, and this basically just aggregates that data together. Does all your base calling on boards, all that fun stuff. But the Mark 1B is basically just this bottom section. When you plug it into any computer that's running an NVIDIA GPU, it runs off the CUDA cores on the GPU. I don't know how much you guys know about computer nerd stuff, but that's kind of my forte. But essentially, you use a graphics card on your computer to do all the base calling real time. And it's just this little dongle about that big.
You need a special computer though.
So NVIDIA graphics card, obviously, you can spend upwards of $3-4 grand on a graphics card and it'll be faster, but I've seen people run it on something as simple as like a $200 graphics card. So, yes.
What are some things that you're testing for in this
So,
project, Leo?
well, we'll go up to our greenhouse and that'll kind of put everything in context more, but, my core function is kind of running the aquaponics lab. So, we're looking at aquaponics, so fish, plant, co-culture. But one of the things that we are really interested in is the bacterial population of these systems are just a black box. No one knows what's going on in there. The nutrient cycling, no one knows about. We just know that nutrients go into fish create waste, the plants take up that waste, and the process starts over. But one thing we're really digging into is what that microbiome is actually doing. So, we're looking at, we're getting an ICP-MS as well. I don't know if you know what an ICP-MS is, but inductively coupled plasma mass spectrophotometer. So, it's a fancy way of saying I can take any sample and give you the elemental composition. Our new unit goes down to, for most elements, 0.06 parts per billion. So, basically what we're doing is tracking nutrient flow through our systems, and with that, looking at the microbiome and looking at specific genes, what's upregulated, what's downregulated, that's specific to like phosphorus cycling, calcium cycling, nitrogen cycling, things like that. So really getting into like the nitty gritty science. So our NSF grant, basically the gist of it is when fish produce waste, it's dissolved, comes out of their gills in the form of ammonia, or it's excreted in solid form. And that solid form has about, just as an example, 30% of the nitrogen that goes into the fish is excreted in solid form. The other 30% is excreted in dissolved form. So when we're talking about nitrogen, that's what our plants want in an aquaponics system, and that's what we're using those plants to clean that nitrogen out of the water, start the process over. But when we remove that solid waste, we're still losing 30% of that nitrogen. So there's a process called mineralization, which is really a fancy way of saying we're composting it, but we're composting it in water. So we use the endemic microbiome in that waste, pull all that waste together, and basically we're using an IBC token greenhouse, aerate it, and we're, over course of a week or two, the microbes break that solid waste down and turn a lot of those nutrients into dissolved, which is then accessible to plants. So one of our students is going to present her research up at KS, and unfortunately it didn't work out as well as we hoped, but the mineralization side worked great, where our starting effluent had, I think, like 10 milligrams per liter of nitrate dissolved in water. After mineralization, we were up to 44. So we had a 340% recovery of nitrogen, which is huge. If you think about for a farmer, you're spending money on that nitrogen, and now we're recovering it. So we're getting to the point where we are, in the actual sense of the word, zero discharge out of our greenhouse. All the waste we keep, mineralize it down, add it back into the system, and so we don't discharge anything now, which is right. From a sustainability perspective, from a financial perspective. And all we're doing is taking an IBC tote, filling it up with fish crap, and throwing air sound in, and letting it run. It's it's really simple, but functionally we don't know how that works. So we're kind of getting into the science of that, what the microbiome is actually doing, testing different pH levels, oxygen levels, like fine tuning the mineralization process for specific nutrients. We want to maximize nitrogen recovery, calcium, iron, and then within that saying, okay, here's the bacteria actually doing it. Can we inoculate the systems with these bacteria? And like jumpstart a bioreactor. So there's my spiel. But sorry my lab's a wreck. Like I said, our equipment's coming in starting on the 20th, so I'm going to take all these shelves off the ICP-MS. I've got to run about 80 amps of 240 for that ICP-MS. Yeah, it's going to be fun. Drill some holes in the walls, fit everything out. It's going to be great. But yeah, so hopefully as part of this grant, this whole lab's basically getting gutted and all new everything. And then we're going to kind of have a core lab over here that we can bring in students to work with. Our next seek someone correct me if I'm wrong, I know everyone's from Kentucky, but it should be, basically the only student accessible medical seek in the state as far as I know. So a lot of the other ones are at medical facilities kind of behind the paywall.
Yeah.
So, you bring them a sample and they'll run it for you, but you never get to work with it. And our goal is to,
That's why I was surprised.
let our students beat up a $250,000 piece of equipment. Good times. But like our program is very hands-on focused. Like that's what we want our students to come out of here with is, hands-on in the ponds, hands-on with the equipment, hands-on testing water quality. So as part of that, we want to start getting into a lot of the next generation sequencing because that's where the industry's going. But yeah, all right.
Cool.
Awesome.
Thank you all for listening to me ramble.
Sheepfish, and going to the ocean and getting the sardine, fish meal fish, it's not sustainable. So we look at alternative protein sources. A lot of soybean meal, corn gluten meal, bone meal. I personally use insect meal for my graduate thesis work. So the big goal of aquaculture nutrition and aquaculture in general is reducing feed costs because fish meal is quite expensive and that dependence on fish meal isn't exactly sustainable. So we're always looking at different sources of protein for our fish feeds. And that's what that laboratory focuses on. We have 32 quarter-acre research ponds, and yes, the buzzards know we're here. Like I said, we've been here since 1999. My joke is that the grandpa buzzard tells his grandkids about a magical place where there's fish abound. And of course we never want anything to pass away, but you scrap a pond out and there's one or two at the bottom, it's not intentional, but it happens. And so, yeah, they know where we are. And we're pretty high in elevation compared to the Kentucky River here. But 32 quarter-acre research ponds, we focus on Kentucky species, catfish, largemouth bass, koi. We have a lot of premier paddlefish work, so American paddlefish, the Poliodon spatula, that's my favorite species that we get to work with here. They are utilized for caviar production, much like a sturgeon. They're just big, giant moo cows. They have big rostrons, they're giant plankton eaters. So they got this big nose with electrosensors on it and they scan for plankton fields. And then get up to 6 feet long, 80 pounds, all you can do to hold one. They're this big. And so we'll wait until they're 5 or 6 years old. They can just go out in a pond, hang out, eat phytoplankton, and we'll come get them in 5 or 6 years and get that caviar from the females. We've also worked on a process that does not sacrifice those females. It's an egg cesarean section in a sense. So we do an incision, an extraction, and then resuture her so she does not get sacrificed. These black containers that you see here is a project that we work on called in-pond raceway production. So our ponds are well suited for aquaculture. You see where our little signs are. We've got all of our ponds pretty much at the top level right now, but there are pipes called standpipes in. So we'll push those down. Always get asked how deep they are. They're about 5.5 foot deep, just deep enough to drown me and my waders if I don't push the standpipe down. But we'll push that pipe down, that water is retained. It goes to one of our reservoirs, our lower reservoirs. So we're not, we want that good biological community that exists on our pond water. So we'll drop that down, we walk around with a seine, float lines on the top, weights on the bottom, and capture those fish. Well then, I would take this into the hatchery, but they're doing a lot of work in there right now, so it's very crowded. There, unfortunately, isn't a whole lot that we can see today in the hatchery. But we'll bring, all those fish from that harvest in. We can sex them, male or female. We can separate them by size. I kind of call that our staging area. So we'll do that, select males and females, and then do our spawning and egg production in that building at times as well. But these allow us to, in a regular farm pond, float this cage containment area. We put a pump on there so that the water continues to flow because, the fountains aren't just to make it look pretty. They're oxygen for our fish. It's essential. So we'll make sure that there's a pump on there, that water is exchanged, that ammonia is exchanged and turned over so that we don't have any water quality pollution issues. And then when you're ready to harvest, you know, it's a lot easier to get them out of this catchment basin. I always get asked about pond turnover. Everybody thinks about, oh man, the pond turnover. That happens usually in the spring and the fall. It's when a rapid shift of temperature occurs often. So 70 degrees last week and it's going to drop to 30. That's when your pond turnover can happen. And then we have instances of dissolved oxygen depletion. So the aerators are important during the day, but they're even more important at night. During the day, those phytoplankton are photosynthesizing, making oxygen. But as soon as that sun goes down, your phytoplankton stops, decay starts to happen, DO can come. So it's even more important that we run aerators overnight to combat that phytoplankton decay that happens after the sun goes. So, yeah, like I said, catfish, paddlefish, largemouth bass. We do a lot of koi work, genetics work. That's what Jeffrey does, a lot of koi genetics and tilapia genetics work. And always trying something different. Different feeding rates, different protein sources, different stocking densities, all types of different research to try to stay innovative. So we're going to head up to the aquaculture. Do you have any questions?
Solar panels are a
That's
joint project with Miami
University of Hawaii.
Hawaii.
Yeah, so we were trying to see, it works in Hawaii, and we were trying to see if solar powered aeration worked in
Aeration. One of them
yeah.
has a battery pack that is and it has
The middle
one
one
that
that
they're
has
actually all
nothing in there, it crashed. When it was super hot, you know, when it was the very hot week, and unfortunately that whole pond crashed. But that's the joy of science, right? You know, you've got to find what doesn't work sometimes. So,
packs are good.
yeah, unfortunately, that didn't exactly work the way we were hoping. But the battery storage, it definitely prolonged the
It's an
Oh,
overnight.
interesting idea.
Yeah. Yep. Yeah, maybe just having good battery packs on there. I'm going to let Leo chat with you a little bit about the greenhouse and its function. It's nice and warm in here. So we have, this is a demonstration scale greenhouse. It is a USDA funded greenhouse. We put out this is deep water culture. And I'll let Leo talk some of the specifics on it just because it's a really innovative project that we have going on right now and a unique new fish species for us.
Yeah, so the primary purpose of this greenhouse is mostly kind of outreach and demonstration. So I would consider this semi-commercial scale. You know, normally if you want to run a commercial scale greenhouse, you put your best together and pack it as far as you go. But the gist is for farmers that are getting started out and say, I want to do an aquaponics greenhouse. Okay, cool. Here's one to scale. You know, I can run smaller replicated systems all day, but until somebody actually has their chance to get their hands on something full scale, they can't really get the gist of what's going to entail. So like Chelsea said, this is a deep water culture system, and all that means is our beds are deep water. Now deep's a relative term, but we're about 8 inches deep.
Good
So
picture for you, friends.
so all the plant roots just hang down in the water. There's no substrate at all besides just
Just one
biofilm that's built up over time. So pros and cons, the more water you have, the more stable it's going to be in terms of temperature, pH, oxygen, all that fun stuff. But you dilute your nutrients down there. If I've got fish producing waste in 100 gallons versus 4,000 gallons, disperse that waste out. So please don't take pictures of my students' ugly tomatoes. This is why we tell them don't run fruiting crops in a deep water culture system unless you plan on mending every day. So we have severe calcium deficiency. Leaves are contorted, tips are burnt. We're still getting good production out of them, but they are not pretty to look at. And that's pretty typical of what we see in deep water culture. Your nutrients get sick.
I must have bad soil because that's really my tomatoes.
Now they're calcium deficient. But they're such a heavy feeder. We've got 8, 10 tomato plants in 4,000 or 5,000 gallons of water, and we're that deficient. I wish we had so we're running a hydro system, a small Dutch bucket system just for demonstration next to it. And we planted tomatoes out at the same time. And the Dutch bucket tomatoes actually look better just because the nutrients are so much more concentrated in a smaller volume. But the way the system works is pretty simple. We've got our fish tanks down the end, which we'll go look at here in a second. We've got some solid waste collectors in the middle. We call them settling chambers. A couple biofilters, degassing tank, so you can get gas built up in there, especially like hydrogen sulfide. If you talk about so degas that off so it doesn't fly the plant roots. Then the water just flows down this bed on the outside, crosses over right there, back up into our sump, pump, push the water out of the sump, back in the fish tanks, process starts all over again. So we've got a couple different types of systems in here too. We've got 3 hydro systems, so hydroponic systems, nutrient film technique system, or NFT. Yeah, the big benefit of this is there's almost nothing underneath these plants. It's a very shallow film of water. So great if you're in an area where it's water scarce. And then the Dutch bucket system, so bigger root zone for plants. Obviously, if I try to put a tomato in the NFT system, the root mass is going to be about 10 foot long and clog that up and flow. And then
It smells so good.
Ginger.
yeah, so we're doing ginger pots over there. And then we have a flood drain system set up for starting out smaller herbs and stuff like that. The flood drain is great for plants that we say they don't like having their feet wet, where they don't like being in water 24 hours a day. So the way the flood drain works is there's a little timer hanging up there. The pump kicks on for about 15 minutes every 2 hours. So the bed fills up with water, floods back out, media retains that water. And like I said, plants that don't want to sit in water 24 hours a day, much happier.
Tubers and others.
Yeah, so we're growing ginger, so all that ginger in the pots over there, we would just set those pots in those flood drain beds. Beds would flood, the media that's in those pots would wick that moisture up. So we're able to grow like a rooting crop without it rotting away, sitting in the water 24 hours a day. So one cool thing that we're doing, I talked about mineralization a bit earlier. So I'll show you guys our IBC cup down there where we mineralize. All these hydro systems are running off mineralized fish effluent. So we're not adding in any kind of like mined fertilizer, which is what you would normally do for a hydro system. You'd be adding in like mined phosphorus, nitrogen, things like that. These are all running off composted fish waste 24 hours a day. Now the only downside we've run into so far, we had this hydro system right here going for a year. We started running into sodium buildup. So where we're not exchanging that water at all, over time we add a little bit of salt, a little bit of salt, a little bit of salt, a little bit of salt. After a year, I think we're basically at, what are we at now, approaching 10% strength seawater in terms of the sodium in there. So getting a little too spicy and have to start all over. But it's a really good run for how long it's in there for. Now in our deep water culture system, the nice thing is the plants will wick a little bit of sodium out over time. And the water's, there's such a big volume of water that we don't get that high concentration of sodium, so the system kind of cleans itself as we go. But in the Dutch bucket systems, they're getting sodium built up. This is part of learning.
Yeah, we focus a lot on leafy greens because they have the long roots, but not super long where it clogs up the channel.
Butterfish.
But we'll try about anything. I love doing flowers in here. I love doing herbs. I like just doing something different and experimenting with unique plants.
We have about
community
agriculture support.
Awesome.
So we'll donate much of that.
Really unique.
Tilapia are the real popular one. They're easy to grow fast, so they just about anything.
It looks like dog food. It's very fish oil. It's really strong fish oil.
But the big problem with
Big pellets.
tilapia, no one wants to eat it in the US. Tilapia market in the US sucks. You're selling for like $4 or $5 a pound if you're lucky. Now, so one of the things we look at, okay, largemouth bass sell for more. Things like that, but they're really aggressive. It's hard to keep them in small recirculating systems. What we're trying right now are sea bass, barramundi.
Huge. We've gotten so
Oh, you have
big.
sea bass too in there?
Yeah, barramundi.
Oh, barramundi
Yeah.
is the sea bass.
They're unique for us. Our first product we got. I love predatory fish. Yeah.
Yeah, well, excuse me, I'm gonna try to fish one out real quick.
I'm super excited to eat one. Like I cannot wait till we're able to eat one. Yeah.
All right, boys and girls, I'm sorry.
I don't know that I've got this one up close.
So they're really goofy looking fish. They have that convex head.
No, you're fine.
So these guys are getting close to like, you know, a small market size fish. So we're about a pound each. The fillets are pretty thick. Come on. I'll back it. Well, I'm here.
They do have spines.
Be nice. Yeah, they do. That's why I'm being ginger, trying to not get stabbed. But yeah, so there's 2 barramundi farms in the U.S. Now, Southeast Asia, they're getting to fairly popular to farm there. But here, there's just no hatchery infrastructure to support them, and no one's really worked with them yet. But, you know, at market, you're looking at $15 per pound as opposed to $4 a pound for tilapia. And these guys have done really, really well. Heat is one of the issues. You know, we're about to harvest them just because these guys will not tolerate cold at all. They need a high temp to eat. They don't like moving. They move worse than any fish I've ever seen. So every time we move them, stock them into a tank, we lose about 25% of them every time. Can equalize temperature, pH, everything.
Yeah, messed up our season. We were hoping to get them in earlier, but we had to wait quite a while to get them stable.
Yeah.
To put them in the system.
So, you know, like Chelsea said earlier, you know, we're all here for research. That's what we're doing. We make mistakes and see what works, see what doesn't. But these guys are growing like pigs. Granted, they're on rocket fuel in terms of feed. That's been one of the big challenges. Is the protein concentration is, you know, 30% higher than what we feed tilapia. You know, tilapia we can get by with like a 32% to 35% protein. These guys are on 45. So when we start doing the math on how that nitrogen cycles through the systems, you know, the amount of plants we need is very different than what these systems are designed for. You know, these systems, almost every aquaculture system in the U.S., all the research is designed around a 35% protein feed tops. So when we start with that 45, I think our nitrate in here is like 45 milligrams per liter now, which is about the highest I've ever seen it. Which isn't crazy in terms of aquaculture, but for plant production, like we're just not taking it out as quick as we need to. So, you know, we're kind of having to rethink what we're planting. Now, the tomatoes will take a ton of nitrogen out, but they also take, you know, calcium, magnesium, potassium, and phosphorus too. And the feed isn't formulated for plants; the feed is formulated for fish. So, you know, iron we always have to supplement. We've got to supplement those other things as well. So, one more thing before we go to the really cool building. This IBC tote over here in the corner is that mineralization tank I was talking about. It looks like chocolate milk, and that stuff. You know, I'd say in terms of nitrogen, if I use that as fertilizer, you know, I could bottle that up.
Lots of nutrients.
Sell that to hydro producers for probably $15 a gallon. So,
Oh.
you know,
How do you supplement the minerals? Is there a system?
So we turn that air off, let the solid settle out. It takes about an hour or two. We end up with an amber colored liquid on top. Pump that wherever it needs to go. So we normally fill up that white tank down there. We fill that up and then just gravity feed the systems with it. So pretty simple. You know, we want to do something that a farmer can do, right? So there's a group out of Canada that's doing like this space station level mineralization tank where it's got peristaltic pumps and real-time monitoring, and it's, you know, puts the pH at like a very specific spot, running pure oxygen line in, oxygenates that to a very specific range. And I'm like, that's great. You spend $100 grand on that. Like, you know, it's
We're bubbling through here.
yeah, you know,
Don't make it harder than it has.
what's a farmer gonna do? They're gonna put an IBC tote, drop an air stem in it, and let it run.
That's
So, but we'll head out. Does anybody have any questions? Got anything up here?
So yeah, this is, so we have 2 main reservoirs, the upper reservoir, this one, the lower reservoir. It kind of pumps our water tower. It pumps from lower up to here, and then it gravity feeds the whole pond.
Gravity feed our pond. We don't have to use the pond.
You see the water. The one at the lower end, what, sustainable aquaculture, what? I know they don't, but like, I did for a while.
I just built it.
Yeah, he had a fancy acronym, but maybe.
Sustainable aquaculture development.
There we go.
Oh, okay.
What's that?
And somehow shrimp is in the hole.
So he does all the marine fish and stuff for it. He does the shrimp, those are the main things. Like converting like pig barns, all pig barns, inflating and putting tools in there, and then doing a biobox system where you're basically constantly increasing
In a
bacteria
pig
growth.
barn.
Yeah, like an old pig barn.
Yeah, that's one of the big things a lot of the indoor
And
farmers
take advantage of those nutrients.
Well,
Or
not, it's all, no, it's just more take advantage of
water
the
a lot
structure
harder
that's
than
already
fresh
there,
water.
and the power, it's
Yeah.
water that's already
It's a
attached
short
to it.
answer.
Yeah, so you're automatically just using that, but then you just insert inside, it's basically a swimming pool, and a pump on it, and then you basically feed it, maybe that's it, usually has a high amount of ammonia and all those situations, a lot of bacteria in it, and then you add
there's a lot more in it,
molasses,
especially for shrimp.
and then it increases the size of bacteria.
Actually, the marine fish, by and large, taste
Yeah. Well, so we've got olive flounder down here right now. So they're a flounder species from like Korea, Japan, coastline.
Increases the weight.
So one of the
I use those instead of
so
brown water just
a lot of the shrimp
Are they
farmers.
tougher?
No, a lot of the shrimp farmers they run marine systems in Kentucky. It's expensive to heat over winter. Shrimp are tropical. So we're looking at like 80 Fahrenheit or higher.
Crowd at the moment,
Yeah.
but so my go made mostly, but we had to bring a lot of stuff in to kind of build it real fast. But we could do qPCR, Sanger sequencing, photometry for protein analysis, electrophoresis, capillary electrophoresis, and all that stuff like that.
In my, Jeffrey's 100% the expert, but my 30-second genetic talk is sometimes we want fish that do not breed. So think of grass carp, for example. If we're using a grass carp to do aquatic weed management, maybe we wouldn't want that fish to breed with a native fish in the system, so we can make a hybrid. And then in my other 30-second poor explanation is male fish make it to the plate faster. So we're gonna act just like anybody else, get fish to the plate, quick as possible, least amount of money. So we can choose to genetically select for all male offspring. We call that YY super males, and they have two Y, an XYY chromosome, meaning that all their offspring are male. That, in theory, so we don't
Nature
have
finds a
any
way.
inadvertent breeding that we don't want to happen, and then also we get those male fish to the plate faster because females have to put a lot of energy in that ovarian egg production. So, isn't that the truth? I know. So we can choose for all male offspring, and that's my 30-second genetics kind of the application for some of those. This is our aquaculture fish production laboratory. Everything in this room is a recirculating aquaculture system or RAS, meaning that we use filters and pumps, much like you do in your swimming pool, to filter out any waste and to clarify that water through filtration and movement through pumps. So I just say it out here because with all the pumps going, it's a little loud up there. I get asked about our water source often. So we get dechlorinated water from the city, and they're stored in those big white tanks that you'll see back there. So we take nothing else from today. If you get a fish and you want to fish at home, don't put tap water in your fish. That's my plea. Yeah, and I wish this county fairs would still giving fish out as fair prizes. This isn't a living animal. I know this isn't a puppy, but it's still a living animal. Come on. Anyway.
Humid environments.
It's always receiving. It's always
change the clothes in here all.
Oh yeah. And we do have showers too.
Oh, we get to
So that big racer right there, the first two, those are salt water. I don't even know.
They are consumable. They are utilized as a food fish. If you go to a crawfish boil, you're getting red swamp crayfish. These are Australian red claw crayfish. So they're unique. If you look really close, my mama does have babies. So look at those tiny, tiny little crayfish in there. See them? I love them so much. So much like an insect, they shed their exoskeleton. So they'll just pop out and be soft and squishy during that. Capacity of this room. We normally have a lot more vertical space being utilized, but we're in the process of building stuff. So this used to have large vertical tanks, and then we are also replacing the system that accompanies this one, so that's why there's a little bit of open space there as well. But our goal is a lot of indoor production of tilapia, and we do a lot of our koi stuff in here. I'm going to show you a really unique species that we have in here. So we have a marine team, a saltwater team as well. We've done shrimp production in the past, and we're moving back into doing marine shrimp production. But right now, we have marine flatfish. So these are olive flounder, marine flatfish, often called Japanese flounder. They're really weird. They have two eyes on the same side. They lay flat on the bottom. They're predatory. But for us, when you look in terms of food conversion ratio, they're super efficient. They come up, they eat, they lay back down like a pancake on the bottom. They don't utilize a lot of energy. I always, like I say, I do a lot of kid tours, so I used to joke and say, we're not salmon in here out swimming a grizzly bear using a lot of energy. Our fish, due to their internal anatomy, they have a swim bladder. Those guys don't, they sink to the bottom. But our tilapia have a swim bladder that allows them to be naturally buoyant. So if you lives in one of these tanks, these fish are just kind of hanging in the water column, not using energy. So the food that we feed them goes into the flesh sometimes because they're not actively swimming against current, trying to not get eaten by a grizzly bear, trying to, swim away from something. They're hanging out, waiting on their next meal, hanging with their buddies. So the flounder, exceptionally fast grow rate, very high market value. They came in about the size of a quarter. Yeah, here's one of the babies. When they came in, that's how small they were when they came in. No, he's preserving hormones. And that's my other favorite babies. These are paddlefish. That's a tiny baby paddlefish. So that big rostrum, they just swim around, giant plankton eaters, and then we'll harvest them for caviar. So let's move on down into the replicated aquaponics before we have to head out.
A lot of our systems. So this system's going to be a marine recirculating system, and all that filtration back there is dedicated to this system. So we're running, we say we have drum filters. Drum filters basically return anti-output water to our water. Run ozone generation to sterilize water, UV sterilization. Big foam fracturators, which is the small one right here. You guys have ever been to the beach and seen like sticky foam blow up? We're harnessing that process and as close to the water, small particles. That's what we care about. I tell people that want to get into aquaculture farming, you're not growing fish, you're growing bacteria. If you can't get the bacteria in there that stabilize your system, you'll never grow fish. So a lot of these chambers, like that black tank back there, some of these poly ones, those are biofilters. And what we're doing in there is that the fish produce waste in the form of ammonia. Ammonia is very toxic. We have to get rid of it somehow. It's dissolved in the water. Can't catch it. Doing it chemically is too expensive, so we do it biologically. So we have bacteria in our systems that basically, if anybody's done ag at some point in their career, they know the nitrogen cycle. They take ammonia to nitrite, nitrite to nitrate. We're doing the same thing in these biofilters. What's that? So in all these tanks, they're filled with these little plastic beads. They look like gears almost. And those are there to provide surface area for the bacteria. So this system, you know, is 5,200 gallons. It's got a 1,400 gallon biofilter dedicated to ammonia removal. Because when we start feeding these fish, there's such a high ammonia input every day that we have to process that, you know, within hours. So yeah, a lot of new systems going in here. We got a lot of stuff that looks like a drum. So the water goes into the inside of this drum, it rotates over slowly, the water passes through this mesh, and then there's a spray bar up the top, sprays back through the mesh, knocks the waste off, and there's actually like a V-shaped trough through the middle, and your waste runs out over here. So, very good at keeping the water clean, not very efficient in terms of water use, but you know, pros and cons to everything.
Well, I figured I would give you a glimpse of the shamu show that we all encounter every morning first thing. They're moving his head. They're not hot enough. Where are they going?
Chelsea, you might be better.
So, greenhouse, you know, allows us to show demonstration of what a full-scale system looks like. But this replication allows us to do statistically valid replicated research. We can test different things like lighting, fish stocking density, you know, different plants. We put those black barriers in between when we're testing different light technologies. Lots of different studies and forms within the system. We can break up the system into individual quadrants and increase our replication even more that. So the same general principle, fish in the square tank, waste, you know, large solid particles come down to that column, those are removed, mineralized area for that bacterial nitrification to occur, and then plant. So that allows us to get all of our data and research into reference scientific journal access. So we just started with a study in there. That's the study that's at KS, that's Acheen's study, the third mineralization project. So we just cleared that out and we're going to get it back running again soon. It stays running pretty much all year long for about the last 10 years, let's say. There's been something going on in here. Yeah, we'll let it kind of chill for, you know, a week or so. And then the flounder that he showed you, they were in those flat bottom things for a graduate project that went quite well. So they had that flat bottom thing. So the majority are in those shapes, and that allows that waste particle to, you know, crack down and easily remove. So they are LED. So we do car meter readings, so we read our car and then choose car based on whether it's a flowering crop or in different staging. We get a hip crop from there. So that's more my reference point where I did different lighting or different staging of the hip. But yeah, we keep on, we can do
They don't get as much. The goal is like more. It's a higher rate. They don't